Hello everyone, this is Dr. Lennon, and we are continuing our study of functions with exponential functions. So exponential functions are functions that behave multiplicatively in the output. So let's go ahead and start down with a definition of the exponential function in standard form. So the definition here, an exponential function is one that has the form a lot of times they will use t rather than x as the input variable because time is such a common input variable, but you could use x instead of t. But it has the form a times b to the t, where a and b are real numbers so we require typically both of these things to be positive, a and b to be greater than 0. And additionally, we don't want b to be equal to 1, because if b is equal to 1, then this would just end up being a horizontal line. So b is not allowed to be 1 either. Sorry, that wasn't a very good one. Let me try and write that a little bit more neatly. So b is not equal to 1. So again, the defining kind of characteristic that you would notice is this is characterized by a multiplicative change in the output. So b is known as the exponential base. And 0, comma a is the y-intercept. So you can see that because if you plug in t into the ab to the t form, you would have ab to the 0, and b to the 0 would just be equal to 1. So we kind of have two graphs that can result from this as a function. Two possible graphs. So what do those graphs look like? Well, there's two cases, one known as exponential growth and one known as exponential decay. So if you have your xy axes here, exponential growth looks something like this. So it tends towards 0 to the left and kind of explodes upward to the right. So this is exponential growth. So this happens when the exponential base b is bigger than 1. If you multiply something in output by a value bigger than 1, it's going to get larger over time. When is it going to decay? So decay looks like the mirror image about the y-axis. Again, this is kind of like the rough shape in general. These things could be stretched or shrunk a little bit. So this is exponential decay. And this happens when b is some number between 0 and 1. So you were multiplying by a half, for instance, you would be getting half the output quantity at each successive time step. So again, maybe we can put those on Desmos to just get a better idea. So if we go to Desmos, we could look at an example of each. So if you look at, say, y equals 2 raised to the x power, we get that graph that's exponential growth, and then the dual would be the exponential decay. So let's kind of make that graph grow away. So if we do y is instead 1/2 to the x, we get something between 0 and 1. So whoops. And we get a graph that is the mirror image about the y-axis. So this is exponential decay. There's kind of an unnecessary parentheses in there. Anyhow, those are your two kind of fundamental graphs. Again, if you would put a number in front, that would just change where it crosses the y-axis. So let's say I put 3 here. notice that makes it hit the y-axis at 3, so you can recognize that that's the y-intercept. So that's what that's doing there. And it kind of changes the shape. It kind of compresses it horizontally or stretches it vertically. Okay, so one question you might ask is, how many points would it take to identify an exponential function? So when we did linear functions, we could say, okay, find the equation of the line through 2 points. How many points would it take for an exponential function? Well, if you look at the formula, again, there's only 2 parameters, a and b. So it turns out, if I give you 2 points and I tell you that you're modeling an exponential quantity, 2 points is enough to find the equation. So let me show you how to do that. It's kind of a nice technique. And certainly I'll be asking one of these on the homework. Sorry, I keep hitting, I meant to write example. Sorry about that. So example. So let's suppose we want to find the exponential function that passes through the 2 points. Sorry, I keep hitting this button accidentally because I'm left-handed on my tablet. So through the points 2, 10 and 4, 75. All right, so basically what you're going to do is our exponential form looks like y equals a times b to the t power. So each one of these points are a t-coordinate followed by a y-coordinate. So what you want to do is just plug each of them in. And the better way to do it is if we plug in the larger of the 2 inputs first. So the second ordered pair 4, 75 is the first one we're going to plug in. So 75 would replace y, and this would be the same as ab to the 4th. And the second pair, 10 as the y value, would be the same as ab squared. So this gives us a system of 2 equations. And then the best way to kind of combine the equations so we only have one variable is, since the right-hand sides both just have a, you can take ratios. Meaning if 75 is equal to ab to the 4th and 10 is equal to ab to the 2nd, we can make this one equation where the fractions will be the same, because 75 over 10 would have to be the same value as ab to the 4th divided by ab squared. So your a's would cancel, and we'd be left with 7.5 equals b to the 2nd power. So remember, again, maybe I should even spell that out a little more clearly. Basically, what do? We subtract the exponents. So we get 4 minus 2, so we get 7.5 equals b squared. Now typically this would have 2 solutions. B would equal plus or minus the square root of 7.5, but in this case, for exponential functions, we require that b be a positive number. So essentially b here is just the square root of 7.5, and let's suppose we're just, well, you could do this either using exact values or approximate values. Let's stick to, well, let's just approximate for this first example. So the square root of 7.5 is about 2.74 if we round. So then we have one of the 2 parameters. So to find the exponential function, we need to identify both a and b. So we've identified b. So now we need to go ahead and identify a. So we know our exponential function looks something like y equals a times 2.74 to the t. And we can plug in either of the 2 points. Either of the 2 points are going to be a t comma y value. So that'll leave us an equation that only has a left. So let's go ahead and plug in 10 for y and 2 for t. So we have 10 equals a times 2.74 squared. And then we can divide by on both sides by 2.74 squared, since that is what a is being multiplied by. So this comes out to about 1.33 is the approximate value of a. So our exponential formula here would be y equals 1.33 times 2.74 to the t power. So that would be the exponential formula. It's an approximation. It's only accurate to 2 decimal places here, but again, I just want to show you the basic thing without getting too hamstrung by the algebra in the first example. Okay, so let's do another one. So same type of example. We want to find the equation of the exponential function that passes through uh, 2,80 and 5,40.96. So similar to the last problem, but let's just go through it again. Again, we know an exponential formula should have the form y equals ab to the t, just by definition. So plug in both points. Again, we want to plug in this point first because it has the larger t value of 5. So we have 40.96 equals ab to the 5th power. And then below we would have 80 equals ab to the 2nd power. So this is our system of equations. We can take ratios. So 40.96 divided by 80 should be the same thing as ab to the 5th over ab squared. So our a's cancel, and if you subtract the exponents, 5 minus 2 leaves 3. On the right-hand side, 40.96 divided by 80 comes out to 0.512. So to undo b to the 3rd power, we want to raise both sides to the 1/3 power. So b to the 3rd is also raised to the 1/3 power. So that works out perfectly actually in this case. 0.8 is our value of b. Okay, so that's one of the parameters. So our exponential formula looks like y equals a times 0.8 to the t power, and then plug in either of the points to solve for a. Doesn't matter which one you plug in. I just typically like to choose the one with the smaller values overall. It just kind of makes the numbers work out easier if you happen to be doing it mentally, or maybe it involves a little bit less writing. So 80 equals a times 0.8 squared. So 80 is 0.64 times a. We can divide both sides by 0.64. So we end up with 125 as our value of a. So our exponential formula in this case is 125 times 0.8 to the t power. So that is the answer there. Okay, so we said that these exponential functions are multiplicative in their output. So when something is multiplicative in its output, it's changing by a fixed percentage. So a question we can pose is, how does the exponential base relate to percentage change in the output? And it's actually a pretty simple relationship. So the correspondence is as follows. If we write the exponential base, which we have been denoting with the letter b, if we write that as equal to 1 plus r, then r is the percent change. So in the previous example, right above, our exponential base, y equals 125 times 0.8 to the t, we have 0.8 as our base, so 0.8 would be equal to 1 plus r, and then you would solve that by subtracting 1 from both sides. So we would end up with negative 0.2 is equal to r. Now that's r as a decimal. So basically, notice since that base is between 0 and 1, we are experiencing exponential decay, which means the output is decreasing over time. So this is telling us the quantity decreases by 20% each unit increase in t. So that's kind of the connection between percent change and the base when we're talking about the exponential formula. So that's the standard form. So now what we're going to move on to is what's known as the continuous form. So any exponential function can also be written in another way involving that special number, Euler's number. So let's go ahead and talk about the continuous form of an exponential function. So the continuous form of an exponential function is given by y equals a times e to the kt. So here our variables are still just t and y. A, e, and k are all constants. And in this case, e is the special constant known as Euler's number, which has approximate value 2.71828 and so on. So this number comes up quite a bit in calculus and also in the theory of interest, and it's next to pi, maybe the most important constant in math. So the main idea is how do we actually switch from standard form to continuous form. So here's our comment. So one can easily translate between continuous form and standard form by setting b equals to e to the k and solving for the unknown parameter. So let's look at an example and see how that goes. Okay, so example. So in the first example, that's all we want to do is convert to the new continuous form from the standard form. So A, let's say we have y equals 300 times 1.12 to the t power. So when we're converting to continuous form, that's all we really care about is this base, this 1.12, and we're trying to figure out how that relates to that constant k. So basically we write 1.12 equals e to the k, and we want to solve for k. So if we want to figure out what k is as a decimal, we have to solve that equation. Now, we're going to talk about natural logs and logarithms in the near future next week, but just know to solve this equation, that's all you have to do is take natural log of both sides. So if you do the natural log of 1.12, that is the same thing as the natural log of e to the k, and we'll talk more about why that is the case in the future, but that comes out to about 0.1133. So if we want to write our continuous form, and again, this is an approximation, so I really shouldn't be using equals, I should be using squiggly equals. because it's a rounded version of the natural log of 1.12. Anyway, so this would be y equals 300 times e to the 0.1133 t. So that is our continuous form of that equation that we saw above. Okay, so let's try another one. What would happen if we looked at, say, y equals 78 times 0.9 to the t power? Again, it works exactly the same way. This time we would just set 0.9 equal to e to the k. Take the natural log of both sides. So the natural log of e to the k is just k. And if you do that in your calculator, you get an approximation of about negative 0.1054. So your continuous form would be y equals 78 times e to the negative 0.1054 t. And this would be your continuous form. All right. So let's continue. Let's go the other way, convert to standard form from the continuous form. So let's go ahead and look at that. So convert to standard form. So let's say if we're given the continuous form y equals 700 times e to the 1.3 t. So now that's all we want to do again is figure out what our base is. So the 700 would remain the same. We just need to do e to the 1.3 in our calculator, and that is going, well, that's exactly equal to b. Once we punch it in, it'll be an approximate value for b. So basically 3.67 is the approximate value of b. So our standard exponential form here is going to be y equals 700, the same y-intercept times 3.67 raised to the t power, and that would be the standard form of the same exponential function. Let's do another one up here. Let's say we have y equals 1000 times e to the negative 0.2 t. So again, same thing, we just need to figure out what is e to the negative 0.2. That's our value for b. So here that is approximately 0.819. So we could write our standard exponential function as y equals 1000 times 0.819 raised to the t power. And there you have it. Okay, so let's finish just talking about a couple of formulas that come up a lot from exponential functions. So these are known as the compound interest formulas. So there's two of them based on the number of times you compound a quantity. So there's the finite compounding version of the formula, which says the future value of an account A is equal to the principal invested times the quantity 1 plus r over n raised to the nt power. So what do all of these things mean? Again, A is the future value. Capital P is the initial investment, sometimes known as the principal. R is the interest rate, and for this formula we want that as a decimal. N is the number of compound periods annually. And the last thing t is the time that the principal is invested in years, so time in years. So for a given nominal interest rate, the more times you compound, the better you're going to do on your investment. But there is a limit to how much you can make for compounding a loan based on some nominal interest rate. So that is known as, if you have a investment that is compounded continuously, so continuous compounding, so what that formula is we just get A equals P times e to the RT power. So again, A, P, R, and T are all the same thing, and E is just Euler's number. So let's go ahead and look at how to compute a few of these. Again, these are just things you plug into your calculator once you know the formulas and figure them out. The only tricky bit is sometimes there's code words indicating the value of n for finite compound interest. So you could have something like quarterly, which would mean it's compounded 4 times per year. You could have it compounded, say, so the common one that you'll see is a lot of companies will pay twice per month. So that would be known as semi-monthly. So if you are paid semi-monthly, you would be paid 24 times per year. Some companies choose to pay every 2 weeks, though. So that would be bi-weekly, meaning you would be paid every 2 weeks. So you would be paid, if there's 52 weeks in a year, 26 times. So a lot of people mistakenly think those two things are interchangeable, but it really does amount to a difference of about 2 pay periods per year. So you need to be a little bit careful when you're watching out for some of those code words there. Okay, so let's look at an example where we just compute some of these things using those formulas. So example, so compute the future value of an investment of $30,000 at 8% for 5 years if, so A, let's say it is compounded annually. So for us, that would just mean n is equal to 1. So if we plug that into the first formula, we would get A equals our 30,000 times 1 plus 0.08 raised to the 5 times 1, which comes out to $44,079.84. Okay, let's go ahead and do another one where maybe we're compounded quarterly. So if we are compounded quarterly, that means n is equal to 4. So in this case, we would have A is equal to 30,000. So in this case, we have 1 plus the 0.08. But now we need to divide that number by 4, and then in the exponent, we're doing 5 times 4. So if you punch this into your calculator, you will get $44,578.42. So notice you're making almost $500 more than A with the same interest rate and name. So obviously, we can see the overall interest isn't going to be the same. That's known as the effective rate. But if they say 8% and then it's got different amounts of compound periods, it's actually going to be offering different effective interest rates, meaning in example B, we're making more money than example A due to compounding. So let's look at C, one more finite compounding case. Let's say compounded monthly. So that for us means n equals 12. So it's going to be very similar to part B. Basically, we're going to use the same exact setup, just anywhere we had a 4, we're changing that to a 12 now. So 30,000 times 1 plus 0.08 divided by 12 raised to the 5 times 12. And then again, we can punch that into the calculator. And again, we're going to get an even larger quantity, 44,695.37. And you can see, even though n went from 4 to 8, we actually ended up with just a little over $100 more, which is less than the jump from part A to part B. So these things do start to level off even as we increase the number of compound periods. So the limit to that is if we compound continuously. So if we look at the same quantity but compounded continuously, we would have A equals 30,000 times E to the 0.08. So we're using the continuous formula above, and that's multiplied by 5. And if we do that on the calculator, we get the largest such value we could have, given the nominal interest rate, $44,754.74. So those are two very common applications of compound interest, which are a form of exponential functions. So that is it for this lecture. We will pick up and do some more examples and applications of exponential functions. So until next time, this is Dr. Lennon signing off.